So let's move on to our next topic. What is your rationale and approach for investing in industrialized construction? We have, there he is, Rafael Coelho. And Iris, are you going to? There she is, Iris Tomlinen. Rafael is an engineering and project management PhD candidate in the Civil Environmental Engineering Department at the University of California, Berkeley. He's a researcher affiliated with the Project Production Systems Laboratory at Berkeley. His research focuses on integrating lean production principles with industrialized and modern methods of construction, in particular mass timber construction, to improve the performance and construction supply chains, thereby enhancing design, engineering, fabrication, and installation processes. Iris is Professor of Engineering and Project Management in the Civil and Environmental Engineering Department and directs the Project Production Systems Laboratory at the University of California, Berkeley. So welcome both, and we'll turn it over to you.
Thank you, Gary. Very much appreciated it, and it's my pleasure to present this piece of work that I work with my awesome advisor, Professor Iris Tomlinen, on industrialized construction. So let me share my screen to get started. And as Gary just said, the title of our presentation is "What's Your Rationale and Approach for Investing in Industrialized Construction?" And this research started with our interest in understanding and really going into the weeds of looking at different industry firms and companies operating in different market sectors in the construction industry to understand why and how they are investing in industrialized construction. But I think to get started, it's important to define what we mean by industrialized construction, and this is one of many definitions that exist, and this one is from the Project Production Institute. The application and use of manufacturing methods and technologies to deliver capital projects, and very importantly, including the use of product development, flow-based production processes, and automation. And I'm sure most, if not all of the audience have probably heard of the terms modular construction, offsite construction, prefabrication, modern methods of construction. And as we understand, those are all under the umbrella of industrialized construction. So, but where and how do we draw the line of what is industrialized construction and perhaps what is not industrialized construction? Very importantly, when we design our production systems, we have to look at the tools and the equipment that we can use to produce whatever it is that we're trying to make. And so we have to look at the right tools for the job that we have at hand. Industrialized construction brings this idea of automation. So we have programmable tools and equipment. As an example, CNC machines and robots that are driven by different pieces of software. The next step is really utilizing artificial intelligence and machine learning so that we can learn from previous performance to better structure our system, to better structure our production. But most importantly, how do we fit these automated pieces of equipment and robotics into a production system so we're not optimizing locally, but we're optimizing the entire production system? So there's tremendous possibilities there, obviously. Again, importantly, industrialized construction is not only about hardware. It's also not only moving work offsite, because we can basically do construction under a roof if we're not looking at production system design and operation science. We emphasize in our paper that purchasing equipment is the easy part. Designing the production system isn't as easy because we have to have a system level thinking or system level view to be able to reap the potential benefits of industrialized construction, including better productivity, lower cost, and faster delivery, and reduced lead times. We need to integrate people and process. We need to look at our production system design. We need to have a skilled workforce. We need to look at our sequence of operations and processes. So after we understand that, we can gradually implement technology both on the hardware side with equipment, robotics, and other pieces of automated equipment, and also on the software side with 3D modeling, with the systems that have to be in place so that our automated equipment can run efficiently and effectively. Very important here, I would like to emphasize the solo paradox. This was a term that came up in the 1980s when computers started to become more common in the workplace. But because it was a new piece of equipment, the integration of computers into the workplace did not really result in great productivity gains, and even in some cases, productivity was worse initially because of poor integration. So this is something that can also happen in industrialized construction. I would say has happened, as we'll see with the first case study in a minute. So it's very important that we'll look at the whole system with an operation science view so that we can really look at optimizing the entire value stream and not only pieces of our systems. There's many reasons why companies are looking at industrialized construction. Some are to address existing current challenges, and here are some of them. And you probably think that some are interrelated, and I totally agree. So low throughput from rework or quality issues, growing demand, and that's related to, for example, space constraints. If I have more demand for my products, maybe I'm a little limited on space. I need a bigger facility. I might look at industrialized construction or automated equipment and robotics for this new fabrication shop. The need to scale to reduce cost. Maybe I have inefficient material handling, I have too much waste in my process, and I look at different tools and different equipment that can help me. Worker safety and ergonomics, and also this one I think is often mentioned, labor shortages. There's also reasons that companies look at investing in industrialized construction so they can be better prepared for the future. So there's automation, there's artificial intelligence, there's so many new technologies, tools, and software in that space. Data-driven insights, so we can, as I said previously, we can look at our existing processes and learn from it and use that data to improve future processes. Some companies want to stay ahead of tech trends so they can be ahead of their competition. They also may want to have new capabilities, maybe build or produce new products to expand their product portfolio. And that could give them a competitive advantage again over their competitors. And also there's push sometimes from investors or executives for innovation. And often investment is a combination of multiple reasons, both from this slide and from the previous slide. So we wanted to go out and look at what different companies are doing, and so we strategically chose 3 case studies, and they're very different from each other on purpose. The first one is Katerra. It's as I'm sure everyone has heard at least the name of this company at least once, and they had this humongous goal of disrupting the industry, but basically end-to-end industrialized construction. So from very early design and engineering all the way through manufacturing, fabrication, delivery, and site installation. So they integrated both vertically through providing all these different services that I just mentioned, but also through the acquisition of existing architecture and contracting firms. The horizontal integration was through their own fabrication facilities. They have multiple facilities across different states in the US, and where they made all kinds of different products. They had more than $2 billion of funding. They were founded in 2015 and went bankrupt in 6 years. So here we're looking at a more business financial, with a more business or financial focus. And what went wrong with Katerra was they did too much, too fast. They were trying to enter all kinds of different construction sectors and different locations, both domestic and abroad. They spend a lot of money and probably ignore variability and demand uncertainty. So they weren't able to execute well, and they weren't able to deliver at the speed and at the cost they anticipated. They overbuilt capacity. They had all those fabrication facilities. So there was a mismatch between supply and demand. And very importantly, we haven't read anything that spoke about Katerra having an operations science perspective to at least first test the market, design their production system so that they could really deliver what the market needed at the time, instead of investing in automation and robotics and all the tech stuff beforehand. And important also to mention that it went through COVID and all the supply chain disruptions that definitely played a part in the bankruptcy, but it for sure wasn't the only reason. Our second case study is really truly in the weeds. So it's an up-close look at the production system of Waters and Wolf, a cladding contractor that is based in the Western United States. They've been applying lean principles and practices over the past 2 decades or so, in both design, fabrication, and installation. So they're very familiar with all the terms and all the ideas of lean and operation science. A few years ago, they decided to invest in a new cutting machine, a new CNC 16-axis machine that could replace 3 of their manual workstations, and they had expectations that they would get better precision, faster cycle times, less reliance on manual labor, and also new capabilities so they could offer new, more innovative products. However, this new machine ended up becoming the bottleneck of the production system. One of the reasons was initially the uptime of the machine, so the time the machine was able to run and actually produce something was less than 50% due to a number of issues. The sensitivity of the sensors was one of them. The machine would stop working when small metal chips would pass by these sensors, so the machine would stop running, requiring people to come and get it restarted. And there's all the time spent with maintenance. And this 40-50% number is compared to what they had before, which was around 90% when they had manual workstations with workers. So even though this new piece of equipment was faster, at least on paper, than the downstream stations, so the stations that came after this machine, these issues and this machine having replaced 3 manual workstations created an imbalance in their production system, which disrupted the flow of production, compared especially to their older production system when they had manual workstations and they had a level workflow across those workstations. So in this case, automation added to the system introduced new variability and consequently reduced throughput. So less production instead of more production, as was the initial expectation. And one more thing is that a piece of equipment sometimes or oftentimes is less flexible than workers that could adapt on the fly, especially when we're dealing with engineered to order or fabricated to order products, which is the case for Waters and Wolf, so highly customized products. So they learned their lessons. So they had to adapt the machine with better lubrication to reduce the downtime, the maintenance time. They changed the clamps and the cutting bits, and they also started 3D printing vices, which are part holders, so that they could speed up changeovers between different products or different curtain wall panels. And this is a lean practice called single-minute exchange of a die. So they learned the flexibility is probably better than raw machine speed and high variety, low volume kind of fabrication, which is the space they operate in. And an operation science mindset could have anticipated the shifting bottlenecks that this new machine would become the new bottleneck. And for the future, they'll be looking at more adaptable and perhaps simpler, less sophisticated equipment. Our third and last case study is Binsky and Snyder. They're a mechanical contractor based in New Jersey. They work on a variety of projects, including in the pharmaceutical, healthcare, and data center markets. This case, I would say, is at a level of abstraction between the Katerra case and the Waters and Wolf case. Not as high level, but not as deep into the weeds as the Waters and Wolf case. They had a high stakes project, a pharmaceutical project about 3 or 4 years ago that served as a pilot for implementing project production management and operation science. So previously, everything was push driven, where the Binsky and Snyder will receive the schedule from the general contract without much input from Binsky and Snyder. And then Binsky and Snyder would produce the drawings, and they would be handed off to the fabrication shop, and the pipes and all the systems and the components, the assemblies would be produced and would be ready before the prerequisites site work was ready, which ended up building an inventory between the fabrication shop and the construction site. So they changed their delivery process. So they created a CONWIP, constrained work in process signal from the field, so they could reduce their inventory between the fabrication and installation. So jobs are only released in the fabrication shop when needed and when capacity is available. So this figure shows that after they create all the engineering data, the 3D models, etc., they create this production packages, which include shop drawings, bill of materials, and very interestingly, bill of processes, which is basically the steps that a product needs to go through, both in the fabrication shop to be fabricated and also in the field to be put in place to be installed. So they also started doing look ahead planning, so 2 to 3 month look ahead plans, and that was combined with the daily and weekly production planning that occurs on the job site, which sends a CONWIP signal from the field to production engineering so that the jobs can be released to the fabrication shop at the right time and be ready for when the site is also ready. So some of the lessons learned from this case, so with project production management and operation science, they started mapping their processes, and not only in the fabrication shop, but also in the field. So they were able to cut the installation time in the field from 130 of 140 days to about 50 days through process mapping, and also looking at fabrication and how they can fabricate assemblies that are easier to install inside. They a few years ago they moved to a new fabrication facility, and they've been using simulation to guide some of their investment decisions. For example, a pipe cutting machine offers a clear return on investment and also a time benefit in the fabrication process. So that's an easy decision for them. However, an automated welding machine, the return on investment and time benefit is not so clear cut, especially because it's not the bottleneck in their current production system. So again, it's important to look at the system as a whole, identifying the bottlenecks of such systems, and then base our decisions or investment decisions according to those criteria. Looking forward, they're trying to optimize the flow across multiple concurrent projects. They usually have several different projects going through their production line at the same time. So it's important for them to really optimize the flow across all those projects, because that's another source of variability. So some of the key takeaways from these 3 case studies: it's really important to understand your production system before making any investment decisions, both your current production system and also your future production system, with automation, with robotics, or perhaps without automation, without robotics, whatever makes the most sense. And each individual case is different. Local optimizations usually do not result in better system flow. Again, it's important to look at the system as a whole and look at the metrics of the system before making local optimization. So design your production system first, and then when you have your system design, when you really understand the system and you will really understand the metrics of your system, you can identify the best or the fit for purpose source of kinds of automation. So as you probably noticed, there's different rationales for investing in industrialized construction. There's also different approaches for implementing industrialized construction, they're not all of them lead to success, or perhaps most of them so far have not led to great success. But it's really important to drive these investments by real needs, right? Both current needs. So look at your demand, look at what products you're trying to make, and look at where you see your company or production system over the next 3, 5, and 10 years, and align that with a clear production strategy that really delivers the products that your customer needs. And again, system level thinking. And what we really want to emphasize with our work here is that operation science and production system design is really essential to realize all the potential benefits of industrialized construction. So that's all I had. Thank you very much, and Iris and I are open for questions. Thank you, Gary.
Very good. I got a question out of the box for you. Was Walters focused on optimizing utilization of their shiny new object?
So, Iris, please feel free to chime in. I think that was their that was their idea at first, because when companies invest in these machines are usually very expensive as well. They can run several $100,000s or even millions of dollars. So when you purchase an expensive piece of equipment, you want to make sure that you can utilize that equipment at its maximum capacity. So you try to basically force everything to go through that new piece of equipment, so that you can reap the benefits and also get the return on investment that you plan. So that's my understanding.
That sounds-
If I may chime in, just maybe modify slightly what Rafael says. I think certainly they did some return on investment calculation, although any return on investment calculation, of course, is driven by many assumptions you have to make, not just financial assumptions about time value of money, but also some understanding of what the utilization of your equipment is going to be. And then there's other considerations, business considerations. Can this machine provide new capability that you didn't have before, for example? As far as directly answering your question, Gary, I mean, my understanding is that they were actually not interested in maximizing utilization of their equipment. I think their question is, can we have, an acceptable level of utilization that warrants the investment in this piece of automation? And they understand flow very well. And so maximizing any part of your flow production system, is looking at the wrong optimization objective, right? It's not about optimization one piece. It's really about optimization, in this case, the throughput that they can achieve to make the very complex types of products that they make.
I guess if you got a current system, if you don't understand how that production system currently operates, you haven't modeled that, making a change to it may result in some surprises. So model the system and then model the change in the system to support decision making. That's what I hear you guys saying.
That's right. And even if they understood the system very well, the system that they had, but they did not fully appreciate, and these are my words, not their words, but I think they did not fully appreciate how much disruption would be caused by making a change.
Yeah, good point. We got a comment. Walters and Wolf, shiny new thing, 16-axis machine sounds exactly like the example of the NCX robotic machine written about by Goldraff in The Goal, published over 40 years ago. It just shows how life can follow fiction. That's made me chuckle. Sounds like it's a pretty close analog, huh?
It's a lesson to be learned and to be learned over and over again.
Apparently learned over and over again. So another question on Katerra. Did you get any insights on how Katerra management missed the boat on exposing and managing their complex production systems?
There's so much going on with Katerra. I think they got, in a way they had way too much money, and I think they ended up spending a lot of effort, for that matters, effort and time and resources, and trying to spend the money, and therefore they really didn't appreciate. They didn't appreciate the complexity of construction business.
Yeah, and they kind of like go big or go home kind of mentality. Sounds like.
And they kept throwing money at it, right? Even though that probably wasn't the problem there.
Yeah.
Like a funding.
Interesting. So if someone's running a company approached you with a desire to transition their operating model to one that's industrialized, where would you advise they start?
Look at their system. Go walk around their fabrication shop and map their processes and look at cycle times of each workstation. Look at their current setup, the number of workers that they have, and the tools that they have for the job right now. Look at the throughput of their system. So look at metrics of the system and metrics of each workstation, and then identify the bottlenecks, map the system as a whole. And then I think the next step would be looking at there's anything out there that could potentially alleviate that or those bottlenecks.
Yeah, and outside of the company, right? What is outside of the company? I mean, where does the company fit within the value stream? And what do other companies provide in the value stream that you can either, buy or, have to make because it's not exactly the product that you want. So the broader value stream you can study, the better decisions you can make.
All right. Tanya, last chance for questions from the audience here. We're running well ahead. We're good on time today, so we can field more questions if we have them. Otherwise, we'll say thank you for your effort to submit the paper and take the time today to present it. We look forward to continue to work with you.
Our pleasure. Thank you for the opportunity.
Thank you very much, Gary.